Hi, my name is Paulina and I'm a software engineer for CrossCompute. CrossCompute is an algorithm marketplace for planning resilient infrastructure and emergency response. We partner with researchers through revenue sharing agreements to help make communities better. In this video, I'm going to be showing you how to create a predictive tool from start to finish. But first, I want to show you how the tool works. This tool is going to test the hypothesis that if there are more libraries around a school, there will be a higher school progress score. Here we have an input field under street name where I'm going to input 102 Dobbin Street and 423 West 55th Street separated by a comma. Keep the same settings and click Run for free. And as you can see, we have a school location table printed with the columns street name, longitude, latitude, coordinates, the library count, some of the library distances, and our final predicted overall score. We have a school location geotable, which is going to show us the points of our school locations or street names that we inputted. And each point that you click on will pull out a row from the table according to the street name address. And finally, we have a score plot image where you will have plotted a bar graph of the library count within 800 meters versus predicted overall score. And then you can click download and it can download all of these results for you if you want them on your own. I think this tool could help perhaps the Department of Education decide where exactly they should build new schools, or also give the general public access to a school's possible progress score given a school's location. Now I'm going to be showing you how to create this tool from start to finish. We're going to log on to crosscompute.com, and having already signed in with your email or LinkedIn, we're going to click Create. We're going to keep all of the settings the same, but you do have the option to click Public so that anyone can see the notebook on your profile. You can keep it as hidden so that only people with the link can see the notebook. You can keep it secure to choose only specific people based on user ID, or you can keep it secret where only you can see the notebook. Also, you have two different types of environments you could run. It could be numerical or computational. To find out the difference, you can click on the link right here that's blue. How much memory would you like to reserve? You are able to choose tiny, small, which changes the numerical CPU memory down here. Medium, 2285, large, bigger, and huge. We only need tiny. And you can also change the amount of time you would like to reserve to the tool. So you can choose 10, 30, 60, 180, or 360. And what settings you choose will affect what it says under how much will this notebook cost. And each setting changes the amount of credits needed to create the notebook. So let's bring it back to hidden. You can see how keeping all the original settings lets us create our notebook for free. But let's change the name of our notebook to Predicting School Progress. We're going to change the time to 60 minutes just so we have enough time to create the entire tool. And click Create. Click on New and Python 3, which will give us a new notebook where we can create our code. This first cell is going to import pandas as PD, and pandas is a library for data manipulation and analysis, which we will have as alias PD so we can use it throughout the rest of our code. We're also going to define a function called load, which is going to take a required argument endpoint URL, non-required argument selected columns equal to none by default, another buffer size equal to 1,000 by default, and another search term by column equal to none. And then our final parameter in this function is going to be a double asterisk KW, which stands for keyword argument, which will allow us to put any number of keyword arguments into our call. And basically what this load function is going to do is take the URL that we give it and any other arguments that we give it, and it's going to take that data from the URL and load it accordingly and add any specifications to the end of the URL and return to us a data frame object in Pandas. Next, we are going to be loading our raw data and go over to our school progress report dataset and click on API, choose a CSV, and then copy this API endpoint to use it back in our code. We will create a new variable called URL and set it to the URL that we just got over from the site. We will create a variable called progress report table and set it to a load function with the arguments URL buffer size equal to 1,000, and then check the length of the progress report table. So here what's happening is it's printing the buffer URL from the load function, and also each time the amount of rows in our table. So the buffer is actually going to help us load faster and see what's loading every time. So here we have 1,000 rows loaded first, and then we have the leftover 715. So that's the values printed here. Next, we're going to write progress report table dot iloc 0, which is a location-based data frame indexing, which gives us a result in a series data type. Here it just makes it easier to see all of the columns on the left-hand side and all their values on the right-hand side, but only of the first row. Next, we're going to narrow our progress table to 3 columns. So we're going to say progress report table equals progress report table and choose the columns DBN, school, and 2010-2011 overall score. And we'll copy it. Then we're going to see what our length is and just making sure that it's the same as before. Next, we are going to drop some rows where at least one element is missing. And do that by saying progress report table equals to progress report table dot drop NA. And now we are going to see how many rows have been dropped. And as you can see, quite a lot. So next, we're going to just check again our columns by saying progress report table.columns and see them right there, because now we will want to rename them. We will do that by saying progress report table equals progress report dot rename. Choose our columns like this, and take that DBN column and rename it to a capital DBN, and then our 2010-2011 overall score, and change it to just overall score. And next we're going to do the following, right? Progress report table equals progress report table dot group by, group it by DBN and get the mean, and then we're going to do progress report table 5. So what we just did was we grouped all the rows where there were multiple rows for the same DBN, and we combined it into one. And doing that, we also found the mean of all the values of those rows that we are combining. So that's why the only rows here are from DBN column and overall score column, because you cannot find the mean of words. So next, we're going to go on to merging school locations by school code. And we are going to go over to the school locations dataset. We're going to click on API, change that to CSV, and then copy this over. Let's name it endpoint URL and set it to the URL we just grabbed. And now we are going to load. So we are going to make a school location table and call load, pass it the endpoint URL, and we're going to set buffer size to 1000 again. And now we're going to see the first 5 rows. All right. Next, we will type school location table.iloc0 to see our output in a series data type, which again shows us all the columns on the left-hand side and their values on the right-hand side. Notice that if you type school location table of the first row and then pick the column location 1, iloc, you will see that the value is in a point form, and we will see later on what this is going to do for us. School location table.iloc of 0 with the column ATS system code gives us the value of the DBN, but with a lot of trailing white space. So we will want to remove it, and we do that by school location table. We're going to rename it here to directly rename the column. We are going to type school location table, then choose its column ATS system code, and we're going to do that .str.strip, which is going to remove any leading or trailing white space, and check to make sure it's removed. And as you can see, it has been. So next, we're going to rename some columns again. And do that like this. Same school location table.rename. Choose our columns like this. I'm going to say location 1 and rename it to WKT, which is the actual name for the value. Location name to school name, because that's actually what it is. And now we're just going to put that all into a new table. Trim school location table, and we're going to just move them over. So DBN, WKT column, and school name column. Now we will be calling on pandas merge, and that will be able to get the trim school location table and combine it with the progress report table. Based on the DBN column because that's what they both share. And now we will check how many rows have been able to be merged. And we have 1412. Now we will just check what our school table looks like. So we do schooltable.ilock0 to get the first index and see all of the columns on the left-hand side and their values on the right-hand side. So next we want to load our last data set from the New York City Open Data website. We're going to go to the library. Click Export and click on Soda API. And as you can see here, it's only giving us a JSON option. So we will click on API Docs and see what options we have from there just to make sure. So here is that same URL as on the other page, and here you can see you can change it to a CSV option. So we will copy this instead and use it in our code. We're going to copy over that URL and put it into endpoint URL. Next, we're going to select some columns this time. And we're going to select bin, the geom, name, and zip. We're going to choose a buffer size of 1,000 again. And we're going to set a variable lib table to the load function, passing the endpoint URL, the selected columns, and the buffer size. And now we will see the first 5 rows of the lib table. So you'll notice that this buffer URL is different from our other ones, and that's because not only did it add that string formatted in the load function for buffer size, but also for selected columns. So basically all the selected columns that we chose are going to be added onto the end of the URL to be able to grab only those columns from the data. So next we're going to prepare the training data set. So we're choosing again our individual sample to be a school. So that means that each row in our data set will represent one school location. We want to predict the school progress. So we're going to have a variable y equal to school table and its column overall score. And then print the first 5 rows of that school table. And then we are going to design a dummy data set. So we will just create a table that will show us what our final training data set should look like. So we're going to name this dummy table and create a data frame like this. Make the first row just 10, 100, 70. The second row maybe 20, 200, 50, and the third row 30, 300, 40. And we're also going to make some column names, which will be library count within X meters, sum of library distances within X meters, and overall score. And see what that dummy table looks like, and here we see it. So the next thing we're going to do is we're actually going to choose feature variables that we will use to predict the target variable, and choose this library count and the sum of library distances to predict our overall score. So we will just print the first 2 rows of the school table to remind us what it looks like, and then also the library table. And we are going to just have a new dataset table, which will just be that school table copy. Check the length to make sure it's the same. Yes, it is. And now we're actually going to do the following. Drop some rows where there are missing values under the column WKT, and check the length now to see how many have been dropped, and actually one has been. So now we are going to get the library count. So we do from Shapely import WKT, and WKT is actually standing for well-known text, and it's a markup language for representing vector geometry objects on a map. So what we want to do is make a function called getXY, and it will take geometry, WKT, and make a variable called geometry, set it to WKT loads the geometry, WKT, and return geometry.coords 0, which will give us an XY. And then we're going to do libxys, set it to lib table, the geom dot apply, get xy values. And what that's going to do is apply the getXY function onto the lib tables, the geom column. And we're going to just print the first x and y's, and here we see it. The next thing we're going to do is from pysal.lib.cg import the KD tree and radius earth km. We're going to have libtree set to KD tree, and we're going to do libxys. We're going to do distance metric equal to arc, and radius set to radius earth km times 1,000. We want to use KD tree because it's more efficient to query the same set of locations, which we are going to do later on. So since we have latitude, longitude, we can use that KD tree implementation that supports geodesic distance metric, or this arc. It also lets us specify a radius, which you cannot do in Euclidean form. So the next thing we do is make a variable called libcount and set it to the length of libtree.data, and we're going to now print libcount. So it's the same. We are going to make a radius in meters and set it to 800. And now we define a get lib count. Take R and have xy equal it to wkt.loads of r's wkt, column dot coords 0, which is going to turn it to xy, and then take distances indices and set it to libtree dot query. So here's that query thing I was talking about, and it's going to take a set of points. It's going to take the number of nearest neighbors, and it's going to take the neighbors within a certain distance, which is going to be, that was 800 meters, and we're going to return the sum of indices that are less than the library count. So the reason we want to do this is because the indices that are marked as the library count are actually going to have a matching distance of infinity, and then we can't use those. So we're going to want to have indices that are actually less than the library count. So we will create a variable updated dataset table. Set it to dataset table.copy and add a new column with the formatted string library count within, grab the radius in meters, apply the get lib count onto that updated dataset table and on its rows by saying axis equal to 1. Now we will look at how our updated dataset table looks like, and as you can see, it has that new column of the library count within 800 meters. So next, we are going to get the sum of the distances. So now we're going to define a function called get sum distance. Take r. Again, we will have xy equal to wkt.loads of r's wkt column and Geocode 0, which will give us xy. And again, we have distances and indices set to the libtree.query, and it will take xy, set k to lib count, and it's going to take that distance of 800 meters, that's in this variable, and return this time the sum of all the distances that have matching indices of less than lib count. We are going to create a new column formatted sum of library distances within that radius in meters, and it's going to be set to applying that get sum distance onto the updated dataset tables rows by setting axis equal to 1. Now we will see how our updated dataset table looks like. And clearly we have a column sum of library distances within 800 meters created. So the next and last thing we have to do is just train this model using the full dataset. So we are going to have a variable x that we will set to updated dataset table. We will have the columns library count within that radius in meters, and another formatted column of sum of library distances within that radius in meters. We will also have a variable y and set it to the updated dataset table with column overall score. And now we're going to get to the part where from sklearn dot linear model we import linear regression. So scikit-learn is a library where we get simple and efficient tools for data mining and analysis. So right now we're going to have a model1 variable, set it to linear regression to create a linear object. And next we're going to train this model using training data from the x and y variable. We're going to make predictions like this using a training set, and we will write 5, 7,000, and 9, 14,000. And that gives us an array of predicted overall scores. So next, from the sklearn.model selection, we will import cross-val score and evaluate an error score by cross-validation. To do that, we type score 1 equals to cross-val score. Model 1 is going to be the object used to fit data. We are going to have to pass an array x, that array y, and we are going to put the number of folds to defaulted 3 and set scoring to the negative mean absolute error. So that is how the model is doing on unseen data. And the mean absolute error is the sum of absolute differences between predictions and actual values. It gives an idea of how wrong the predictions were. And if you want any more information on the CV number of folds, which here splits data into 3 subsets, I have a resource linked down in the description below. Now let's print score 1. I have to write here this mean. Yes, so now we get the mean. Next we're going to import pickle, and that lets you serialize objects to byte streams. And we are going to use the dump function to write a pickle representation of the object to just a model.pickle file with writing binary permission. Now that we've imported pickle, we actually want to dump some variables into another pickle file. And specifically, we want to dump from these definitions the libtree and libcount variables, because we will want to use them in our next file to get the library count and sum of distances for each address that the user inputs into the tool. To do that, we will use pickle.dump, and we are going to put libcount and libtree into a list, and we are going to have open vars.pickle and also give it the right binary permission. Now we are going to go home, and you will see that seconds ago the vars.pickle file was created. Now we will go back to our file to make sure we give it a name. we can name it Prepare Training Dataset to Estimate School Progress from Library Count. So now that we have that all set, we can just take that and close it and create a new Python 3 notebook. Now the reason that we are creating a new notebook is because we want to separate the code for all the work we're doing behind the tool, and we want a separate notebook for all the code that we will write for the tool interface or design and how it will appear to the user. With our notebook for the tool, we will also be able to use the 3 buttons above, these 3 buttons here. The first Y button, you're able to back up your notebook. The second blue button, you're able to preview your tool. And then the last red button, you're able to deploy the tool. And that means you will be able to publish it on the website for people to see. The preview is just so you can see before you decide to commit your work. The first thing you need to do when you are creating your tool in the notebook is write hashtag CrossCompute. Without this line, without this comment, you will not be able to preview or deploy your tool in the browser. Now we need to make a variable called target folder, and we are going to set it to temp. We are also going to make a variable called street name, which we will fill for now with the street names 102 Dobbin Street and 423 West 55th Street. The next step is to load your arguments. We're going to import pandas as PD and make a variable called street name split that will split the street names in the street name variable by a comma and store them. Now we will make a variable called address table and make a pandas data frame of the street name split with the columns street name. And this is just going to create a address table, a table with each street name as a new row in the table under a column street name. Now we want to render the map. I'm going to create a address table, address geotable variable, and we're going to set it to address table copy. This will just prevent the setting with copy warning. Now we want to geocode address locations, so we will from GeoPy import Google v3, make a variable geocode. We will set it to Google v3 with following token dot geocode. We'll define a function called get longitude latitude of a row, and we are going to make a variable called location, set it to geocode the row's street name, and this will let us get the longitude and latitude from location. So for each row we will have a new longitude column, set it to location dot longitude, which will give us the longitude of the street name address, and then a new column called latitude for each row, set to location dot latitude. Finally, return the row. And to make it a little bit more detailed, we will make an if statement. If the length of address geotable turns out to be greater than or equal to 1, then that means that the user has inputted at least one street name. So we are able to apply the get longitude latitude function on each row by specifying axis equal to 1. And finally, we can see what our address geotable will then look like. And as you can see, we have a new column longitude and latitude for each row that we've gotten from geocoding the address locations. Now we want to create a new column in address geotable called coordinates. That will be a tuple of the longitude and latitude by doing list zip address geotable longitude and address geotable latitude. We are able to combine longitude and latitude to be under this one column coordinates. To see what it looks like, we will print the address geotable. And we have this new column coordinates with a tuple of longitude and latitude for each row. Next, from pickle import load, we want to load libcount and libtree. We will make two variables libcount, libtree, and load from the vars.pickle file with read binary permission the values that we stored from the other file into this vars.pickle. Going to go home, and if we click on prepare training dataset file, it will be easier to do the following. We will now need to get the library count, same way as we did in this file. So we will go back to the libcount function. We can just click on the cell and copy it over. So after we do this step, we want to just copy that cell directly, but instead of setting xy to wkt dot coords, we already have it in coordinates form because of our new column. So we will just get the rows are coordinates from the coordinates column. Now we will add a new column to our address geotable with a formatted string library count within radius and meters, and set it to address geotable, applying the get lib count onto the rows. To see what we just did, we will print the address geotable, and as you can see, for the first address that we've inputted, we have one library within 800 meters, and for the second we have two libraries within 800 meters. That's what this column means. After we've gotten the library count we need to get the sum of distances. So we will go back to the prepare training dataset file, and we will now copy the get sum distance function. Clicking on the cell and then just pasting, but instead of this line, we will set XY again to our coordinates. And we will also make a new column in address geotable with the formatted string sum of library distances within radius in meters, and we will apply the get sum distance on the rows by setting axis equal to 1. And to see the changes that we have just made, we'll print the address geotable once again, and we have now values for the sum of library distances that are within the 800 meters of the address in the row. After we finish that, we need to run the model to estimate the target variable. So to load the model, we from pickle import load once again. We set a variable model to load. We open the model.pickle file this time, and also give it read binary permission. And to see what that variable gives us, it's a linear regression. To run the model, we make a uppercase X variable, set it to address geotable. We will use the library count within 800 meters column, and also sum of library distances within 800 meters column to use their values. And in a lowercase y variable, we will predict the school's overall score using the values from the column's library count within 800 meters and sum of library distances with 800 meters from the address geotable. And to see what y will give us, these are the predicted overall scores using the library count and the sum of library distances for each row in the table. Now, to add the column with those values, we write address geotable, predicted overall score, and set it to y, the array of the numbers. And now to see how the added column looks like, each value from that array was put into each row of the table. After we have added a column for the predicted overall score, we will want to render the first result for our tool. We need to save the file to the target folder to include it in the result download. So we will have a target underscore path variable that we will set to target folder plus a dot CSV. We will have address geotable to CSV, target path, index set to false, and to render the table, we need to print the table path. We will write school location table path and set it to target path. The next thing we will do is set the radius for the point of each street name. For the tool's map result, we will write address geotable, radius in pixels, range 10 to 20, and address geotable, library count within 800 meters. We will set the color for each point using a rule. So if the length of the address geotable is in fact greater than or equal to 1, then we can create a fill color column for the address geotable that will apply this function, lambda, which allows you to write an inline function instead of creating a separate function and calling it. So for each row of the address geotable, we will put R if the row's predicted overall score is going to be less than 50. Otherwise, else, we'll put G. And specify the row's axis equal 1. To see what we did, we will print address geotable. Since both scores are 50 or above, we assign green for fill color. Now we want to save the file to the target folder. To include it in the result download once again, assign to target path target folder plus b.csv this time. For the next kind of result, we will address geotable to CSV with target path and index set to false once again. And we print the geotable path to render the map with the formatted string school location geotable path equals target path. And finally, to render the last type of result, when we run our tool, we render the plot, which we create by %matplotlib inline. We have a variable axis that we set to address geotable with bars for library count within 800 meters, as well as predicted overall score. And we plot kind set to bar for a bar graph. And here you can see the results as a bar graph. For this last result, we need to, for the third time, save the file to the target folder to include it in the result download. So we will set target path this time to target folder plus c.png. We will have a variable figure. We'll set it to axis dot get figure and figure dot save fig with that target path. We can print with the formatted string score plot image path, and we'll set it to target path. That is the last line that we need to have our tool ready. So if we preview this tool, you click the blue button, and you click here to access your tool. Right now you will see this line is filled with the addresses that we inputted in our code when we were writing it. The reason we were doing that there is because we wanted to see these results. You wouldn't be able to see the results as you're typing if you did not have anything here. And also, we have untitled on the top. So let's close this, and since this is the file or notebook that correlates to the tool, the name of the tool will be the same as the name for this notebook. So we should change the name from untitled to something specific to your tool or a summary of your tool. So we will write predict overall score by address. Rename. Also, we want to remove what we have in the street name so that we can type what we want in our tool. So if we preview it once again, we have an empty street name, so you can input any address you like, and we now have a name for our tool. Let's say we put in the same addresses, 102 Dobbin Street and 423 West 55th Street. If you run it, now you have a school location table that looks just like what we saw while we were coding in the notebook. And we also have our school location geotable with both points plotted green because each point's overall score was either 50 or above. You can see over here. If you click on each point, you will get the corresponding line from the table. So this point belongs to the address 423 West 55th Street. And if you find the other point, it is going to return the line from the table that has the street name address of 102 Dobbin Street. Finally, you have the score plot image, and you have a download button to download each result separately to your own computer. Now, if we close this and we go back to our predict overall score by address notebook, we can now click this red button to deploy our tool. If you click here to access your tool, then you will see how your users are really going to see the tool. This would be the link that you could share, and they will have to type in the street names under street name here. In our case, we can continue to do 102 Dobbin Street, 423 West 55th Street, just to see the same results all over. And then we will just click run for free. When the result is ready, the result will show right under. You have your school location table, same as the preview, your school location geo table with green points. And then they correspond to rows in the table according to the location of the address, and you finally have your score plot image, which you can also click download and receive everything in your local computer. This is how you create a predictive tool on CrossCompute. I will also link the notebooks and finished tool down below. I hope you enjoyed this video. If you want to see more tools, you can go on www.crosscompute.com. If you have any questions or topics you would like to be covered next, please leave a comment down below. Thank you for watching.